Look inside any modern device, from the compass in your smartphone to the hard drive in a server farm, and you will find sensors relying on magnetoresistance. Magnetoresistance, or MR, is the physical property that dictates how a material's electrical resistance changes when it is exposed to a magnetic field. Physicists have been studying this effect for over 150 years. Early experiments mapped out the basic relationship between magnetism and electricity that eventually made high-density digital memory possible. This diagram shows the core physical rule for achieving a massive magnetoresistance response. To get a high signal, electrons must possess extreme mobility, flowing through a material with minimal collisions. For decades, achieving perfect flow meant cooling materials down to near absolute zero. But engineers face a strict thermodynamic barrier at room temperature. Heat causes atoms to vibrate, which scatters the electrons, plummets their mobility, and drops the MR response to a tiny fraction of a percent. Heat breeds atomic chaos. This physical reality has stood as a hard limit, preventing the creation of hypersensitive magnetic sensors for everyday environments. To bypass this barrier, a research team at the University of Manchester decided to abandon standard metals. They turned to a single layer of carbon atoms, monolayer graphene. This lab is known for exploring the extreme limits of 2D materials. They knew that graphene theoretically possessed incredible electron mobility, but it is notoriously fragile when exposed to the environment. To protect the graphene, they sandwiched it between two layers of hexagonal boron nitride. Hexagonal boron nitride is an insulating crystalline material that provides a smooth, defect-free surface for other 2D materials to rest on. Once the device was sealed, they tuned it to the neutrality point. The neutrality point is the exact voltage where a material has a balanced number of positively charged holes and negatively charged electrons. At 300 Kelvin, roughly room temperature, the electron mobility didn't die out. Instead, the thermal energy excited the particles, transforming them into a Dirac plasma. A Dirac plasma is a unique, charge-neutral soup of interacting electrons and holes that behave as if they have no mass. The researchers used the same thermal energy that usually destroys electron mobility to activate a highly sensitive state of matter. This graph illustrates the first major result. When the team applied a small magnetic field of just 0.1 Tesla, the electrical resistance of the Dirac plasma spiked by 110%. That response is orders of magnitude higher than the magnetoresistance recorded in any other known material operating at these temperatures. This result is a direct consequence of the plasma's fluid mechanics. When you apply a magnetic field, cyclotron motion forces both the positive holes and the negative electrons to drift in the same direction. Because both particle types are traveling together, their collisions do not cancel out the current. The impact doesn't slow down the overall electrical response. By acting as a mass-free fluid, the Dirac plasma bypasses the normal rules of thermal friction. The heat remains, but the resistance it typically causes is overcome. The team then pushed the experiment further, ramping the magnetic field up to 10 Tesla and beyond. At this stage, the smooth parabolic curve breaks. The resistance surges in a perfectly straight linear trajectory, eventually hitting a 10,000% increase. To determine why the physics changed, the team used a technique called proximity screening. Proximity screening is a method where a nearby metal layer is used to absorb and weaken the electric interactions between particles in a target material. By placing a metal gate just a few nanometers above the graphene, they soaked up the ambient electric fields. Almost immediately, the massive linear spike in resistance was suppressed. That suppression confirmed the linear spike was driven by intense quantum interactions. The magnetic field was so strong it forced all the electrons onto a singular state known as the zeroth Landau level. The zeroth Landau level is a quantum state where particles in a magnetic field are restricted to a single stationary energy tier. Because the screening dampened the effect, it proved the researchers had isolated a controllable quantum state rather than random noise. We now have a material that is over 100 times more magnetically sensitive at room temperature than current industry standards. A shift in sensitivity this large opens up immediate engineering possibilities. It provides the foundation for microscopic magnetic sensors that can track battery flows in electric vehicles or monitor faint biological signals in medical devices. Beyond consumer technology, this gives physicists a new tool to study a baffling class of materials known as strange metals. Strange metals are a class of quantum materials that defy the standard laws of electrical resistance found in ordinary metals like copper. Materials like high-temperature superconductors also exhibit this straight-line magnetoresistance. However, their three-dimensional structures make them difficult to isolate and study in a laboratory. This graphene-based device provides a pristine two-dimensional sandbox. Physicists can now tune the heat, adjust the magnetic field, and directly observe how these quantum interactions play out in real time. Nearly 2 decades after it was first isolated, graphene is still revealing new physics. It proves that turning up the heat does not always result in atomic chaos. Under the right conditions, it reveals a different set of physical rules.